this wonderful perspective from a material chemical science perspective. So yeah, if you have any questions, please post it in the Discord. Discord once again. Okay, then let's move to the next speaker, Dario. Please share your screen and.
Yeah, I think the other one should stop sharing and then I can share.
Okay, stop. Yeah.
Okay, very good, thank you. And let me share. Okay. Can you see my full screen now?
Yes, go ahead. Yeah, thank you.
Great, excellent. Thank you, Fumia, for putting together this beautiful set of speakers and all these friends and new people. It's great. And thank you for having me here. So I was torn about what I'm going to say in this workshop. And I decided to focus on one very specific message. And it's about morphological computation. So embodied AI has a number of specificities. One of them certainly is leveraging or developing artificial intelligence together with the morphology, with the materials that these robots are made of. So there is this sensory motor loop that we cannot forget when we develop AI. But another important tenet of embodied AI is what is often called morphological computation, which means delegating some of, or simplifying some of the computation by delegating that to the materials and to the morphological properties of the machine, which is something that happens very often in nature. And there are a few cases around. What I want to show to you today is some very specific cases of this simplification principle through morphological computation in the field of aerial machines. And I paraphrase here the title of Milan Kundera's book, The Unbearable Lightness of Being Here, The Unbearable Lightness of Drones. What does it mean? Drones are, aerial machines in general, are challenging to develop because they must be lightweight to be relative to their battery and motors. They must be lightweight because they must fly. So you cannot put simply a lot of computation, computers and sensors on board to make them smart or intelligent. Second, as they move very dynamically in 3D space and they can interact with the environment, they can be very difficult to compute. So they require a lot of computational effort and a lot of AI and control theories is developed to that. Now, what I want to show is that by leveraging morphological computation, you can make this unbearable lightness a bearable lightness. And I want to start with one example. The example is the control. So we know, for example, that controlling drones flying in cluttered environments can be very complex, and there are a lot of people doing very smart things today with a lot of computations, but insects do it very simply. They use optic flow, they leverage optic flow through their compound eyes, which you see here. These compound eyes come in different shapes, and there are essentially a lot of eyes that point in different directions, as yesterday Barbara Webb was also mentioning. And the computation behind these eyes is extremely simple. You see from this, from Laughlin here, there are a limited number of cells that are taking input from specific eyes pointing in specific directions, and they are translating those inputs into a motor command. So you have a number of neurons, for example, the housefly has 13 number of neurons that are responsible for causing specific actions of this insect. So they don't have to have deconvolution of the images, analysis of what happens in the images. They very rapidly go from the motion signals coming from specific directions where they look at into 3 synapses, into actions, which is very fast. And so in the past, so with my collaborators, Jean-Christophe Zuffray and Antoine Beyeler, we developed a small compound camera. What you see here is just 6 sensors. Each of these sensors is a small mouse chip, optical chip like this one, that can detect motion and has small optics, so it can only look in one direction. And you see, this is the front of a drone, so we have one chip pointing downwards and the other one pointing on the side. And we used only 2 neurons that take input from these different cameras, and one neuron is responsible for controlling the altitude, and the other neuron is responsible for turning left and right by rolling the plane. And by doing that, so this is literally just 20 lines of C code, we have this drone that is capable of maintaining altitude, avoiding anything within the field of view, You see here, then gravity puts it down, there are no obstacles in the sky. And it does this so fast and so efficiently. Now we in a collaboration with colleagues at University of Marseille, including Stéphane Violet, who is here with us today, and people at Fraunhofer Institute, we developed then a scaled down version of these compound eyes with 700 eyes that mimic precisely the Drosophila visual system with a weight of less than a gram and a thickness of less than a millimeter, giving them 180 degrees field of view. Now it's still larger than a compound eye, but it's 10 times faster than the eye of these insects because we use electronic speed. Now you say, okay, great, what do we do with all of this? Well, if you can measure altitude and regulate things, at that time, oh, by the way, this is a fossil compound eye that was found in trilobites, 200 million, was used by these animals 250 million years ago. They were living on the seafloor. So interestingly, some of the first compound eyes look like our cylindrical technological compound eye. But what I want to say is that at that time, beginning of 2010 or so, we started a spin-off company called SenseFly. Today is part of Parrot Group. And at that time, GPS signal was not very good. So these drones were used to, and they are still used for mapping for agricultural purposes. But one of the problems of drones with wings is that when they fly back, they have to use GPS for landing, and GPS is not, and still was even worse at that time. So the drone would crash or would land far away from the person who launched it. And thanks to the integration of this very simple technology, which is super fast, when the drone comes back to the operator, it uses the optic flow to regulate the altitude, and we could ensure it would land within 5 meters of the person. So this made a difference. And the company was very successful. Now I'm no longer part of it. I'm not sure if they use it, but still this company is the leading drone company in the world for aerial service in agriculture. So there is a use of this morphological computation. But even if you have the best compound eye or the best camera today, you may, if you fly in very cluttered environment, more than this cluttered environment, you may collide with obstacles. And there is a lot of research recently using stereo cameras and algorithms for trying to avoid situations where a drone would crash and fall on the ground. And then some time ago, one of my students, Adrien Brio, was performing part of his master project in Harvard with Robert Wood, and he developed a camera for measuring what insects do when they are in very collided environment. And when he brought back this image, I was struck. I said, look, the insect collides with surfaces and obstacles, but instead of falling to the ground and breaking as our drones do, they simply absorb the collision thanks to the exoskeleton, which, as Barbara Webb said yesterday, is not soft, but it is flexible. It absorbs the collision and the insect keeps flying. And so we translated this very simple concept.
The novelty of this platform is its rotating protective frame. It decouples the inner frame with all the stabilization system and avionics, so that when a collision occurs, the inner frame remains stable and only the outer frame rotates. To test our robot, we flew it completely autonomously through a forest. We just gave it a magnetic direction, and without any obstacle avoidance technique, it was able to fly for several hundred meters while encountering multiple collisions with trees.
Okay. And so again, this was very simple about translation of biological principles into engineering, but it made a difference. So Adrien eventually started this company called Flyability, which today is the leader for inspection in confined environment. So again, morphological computation simplifies control and is very useful. Now, let's look at fixed wings versus multicopters. There has been a lot of progress over these years, but the differences remain. Fixed wings for the same mass, they fly almost double distances, multicopters, which have instead to sustain their own weight to fly. However, fixed wing drones take some space to do turns. They are not very agile. Instead, multicopters are very agile. And so people in fixed wing community are trying to work out fixes to this. For example, they are now developing control systems so that these drones can behave like helicopter and gradually land on the tail. And people working with multicopters, they try all sorts of different computations for making them agile. But if you look at nature, you have birds of prey, which have extreme agility. They use wings so they can cover longer distances, but if they want, they are extremely agile in changing their trajectory very rapidly. And the way in which they do that is that they morph their body quite a lot. They change the aerial surface to locomote in different wind conditions in different environments. So with Stefano Minchev, who is now a professor at ETH, we developed a principle of adaptive morphology, which there are lots of examples from nature where animals change their morphology to adapt to different environments instead of changing their control. And so here you see what we want to do. We want to achieve these days a drone that has the agility of these goshawk, these birds of prey. Look how they change the morphology of their wings and of their tail to fly in different conditions through obstacles. Look, the entire body even changes. So we designed a new drone which has morphing wings and morphing tails made of artificial feathers. And we show that just because of the morphing of these wings and the morphing of these feathers in an infinite number of ways almost, this drone can, without complicated control, generate super agile trajectory that no fixed wing drone, not even acrobatic drones, planes can. And at the same time retains the same agility of multicopters. And now the problem is that now here it starts to become interesting, because here controlling this drone is super difficult. My PhD student Enrico is a very proficient pilot. He's remote controlling this drone, but this is now where we need to have embodied intelligence that leverages all these and harness all this complexity. But controlling drones is not easy. I'm still very bad at controlling my drones. And if you look at the best drone pilots, they are in drone racing, what they do is that they use these joysticks and this first-person view perspective from the drones. You ask them, do you feel like flying? No, they say they are not flying. They are controlling these machines. Why is that? Because they use remote controllers into robotic interfaces that have been designed with the old way of thinking of the control system. You have perfect control. You have a lot of cognitive process going on in the brain. And it requires a lot of training. So we said, hey, what about embodiment? How would humans fly if they could fly? And so what we did is that we presented, in collaboration with my colleague Silvestro Micera, we presented human subjects perspectives from drones flying, and we let them, we didn't say, this is a drone. We simply said, hey, just try to reproduce with your body what you see so that maybe you reproduce the same actions. So essentially we tested people in different conditions with pictures coming from winged drones, from quadrotors, which have different dynamics. And we put them sitting down on a stool or laying down on a bed like a bird, or standing, and we measured their kinematics and their muscular activities. And out of this, Jennifer, the lady you saw in the image before, she extracted the most important aspects of the motion of the body and the muscles that allowed us to design what we call the fly jacket, which is a mechanism which is a wearable soft exoskeleton that you put on your body. You see the images from the drone, and just you move your body. This wearable measures your body movement and translates that into control. And the incredible thing is that in the worst case, this flying jacket that uses simply the motion of the body is as good as a remote controller for the expert pilots. But number two, a lot of people can fly immediately with no training a complex drone. We tested this with more than 600 subjects, in Boston, in London, in Zurich, different exhibitions. People from all ages, they put on the jacket, they do not know how to fly, they feel fly, and they feel like flying. I think my time is over, is that right? So I think I'll stop here, but it simply shows that embodiment is also useful for rethinking how we interface with the machine. Thank you.
Okay, thank you, Dario. I think this is a wonderful topic for discussion later, and it has a lot of synergy with the Takashi Kigami's talk as well, right? Yeah, brilliant. Thank